Um, I don't know. There's the list of homework assignments. So that hasn't changed since last time. So um, you guys finished the quiz. This one, no, yeah, that one. So that one's done. And um, but if you did that, since that was due Monday, um, you if you, but I think everyone has worked on that. But if you haven't, then remember you still have, even though it was due Monday, you still have a couple of days right after the due date. So you would still have to midnight tonight to work on that and um, earn points if you didn't get any points to start with. Or you can earn additional points. But it's going to be probably hard to improve your score now because on the quiz, because you'll get a penalty, right? A late penalty. Um, so if you've already done it once, you probably won't be able to beat that score with the late penalty. But if you don't have any points for that, then it's worth taking the quiz for sure. And then we have a homework due tonight, right? So more to the point here, we have this homework 2.3 that's due at midnight, all right? So, but I think we are ready for that and also for the next homework and quiz because we're going to finish chapter 2 today. We just have actually to finish one example. And then we're going to do our activity that actually is about that example that we're finishing that we started last time. This is about piecewise linear functions. That's our last little topic in straight lines. And then we get to go on to chapter 3. And it'll still be about functions, of course, but a different type of function. So we can get off linear functions and onto something new. If you don't have the worksheet, did you pick up the worksheets, Taylor? Yeah, if you didn't bring back that activity, I think it's 5. Is that 5? Yeah, then I have some extra copies, so Taylor will give you that, so we can work on that right when we finish this example. Do you guys have any questions that y'all want to ask? So almost everyone did the quiz, so that was good. So keep participating in the homework. That's really important, obviously. In order to get ready for, that was the main thing I was going to mention. In order to get ready for the test, right, which is a week from today. So, and I already told you last time and sent you guys an email that the sample test is posted, right? So now's the time to be working on the sample test, and there's the sample test. So now's the time to be working on the sample test, and use that sample test as a guide to help you prepare your survival card, right? So things that you needed for the sample test, formulas or hints or problem examples, even whatever you can fit on that standard size index card, right? Use that sample test to help you make out the survival card, okay? So really spend some time with the survival card. If you didn't last time, then you don't want to make that mistake again, right? And of course, spend some time with the sample test, right? So that's a really key strategy to doing well on the test. So I want to again encourage you to go to the Math Center. All right, make use of the Math Center. You're paying for that indirectly, at least. Actually, kind of directly. You're paying for that. So you want to exploit that service, right? So take that sample test to the Math Center and work there on the sample test so you can ask questions. And when you have homework questions that are challenging and you're having difficulty, answering it correctly, then take that homework, right, also to the Math Center, okay, and ask them, right, so you can score really high on your your homeworks especially. Quiz is a little bit harder to score high on, right, because you have to take the whole quiz in one sitting. But the homeworks especially, since you can ask for similar questions, right? You know, if there's one that you're not getting, go to the Math Center and do it there, right? So that they can give you some assistance, right? So you can get a really high score on your homework. Those same questions that are causing you issues on your homework, of course, are going to probably show up on the test, and they're going to, you know, you don't want to miss them on the test, right? Where the points really do hurt, okay, your average. So again, make use of the Math Center. All right, so there's the sample test. We have this one example to finish that we were started last time, but we didn't get very far into it. And this is our second example of a piecewise linear function, right? Okay, and a piecewise function doesn't have to be linear, but these examples that we're looking at are linear. But what makes a function piecewise is the formula for the function has different pieces, correct? So here's an example of a piecewise function that's got two pieces. And so you're going to use one of those two formulas to evaluate the function, right? And which of those two formulas you use depends on your input. So you can use this guide, right, on the right-hand side of the formula to choose which formula to use, right, to evaluate the piecewise function. So we tried that last time with these three inputs, okay? We're going to use those inputs again in just and outputs again in just a second, because we're actually going to graph this piecewise function. So for instance, to evaluate f of minus 4, right, we used the first formula because notice minus 4 fits this inequality, correct? Minus 4 is bigger than or equal to minus 4. Of course, it's also less than 2 as well. So since minus 4 matches that inequality, then we'll use this formula to evaluate f of minus 4. So we got f of minus 4 was minus 4 minus 1, which is negative 5. And then we also evaluate f of 0. I think we also use the first formula because 0 is between minus 4 and 2, right? So using that formula, when you evaluate f of 0, you get negative 1, right? But for this next evaluation, f of 2, we wanted to evaluate f of 2. Let me see if I can position this correct. Yeah, okay. Since 2 matches the second inequality, not the first inequality, right? Remember, we used this formula to evaluate f of 2. So we got minus 2 times 2, which is minus 4, all right? So now we want to actually make a graph of this piecewise function. So this function is called linear, piecewise linear, because both of the pieces of the function formula, the x minus 1 and the minus 2x, both of those are going to be straight lines. So when you graph x minus 1, you get a straight line, right? And when you graph minus 2x, you also get a straight line. So when we graph this function f, it's going to have two pieces, both of which are straight lines. So so let's convert this to a graph, all right? We already know, have an idea, right, what the graph is going to look like. Let me see if I copied that. Let's copy this formula. Down here with our graph so we can see it a little bit better when we're making the graph. Let me see if I can squeeze this in somewhere. Okay, well, we'll try it right there. All right. So so we actually want to build a graph there of that piecewise function. So we had remember though, we had already evaluated the piecewise function, right, for some inputs. So let's make use of that work that we've already done. So remember, before we had evaluated f of minus 4, right? And that had turned out to be minus 5. And we had also evaluated f of 0, and that had turned out to be minus 1. And we also had evaluated f of 2, and that had turned out to be minus 4. So these evaluations are going to help us make the graph because they tell us some points, right, that are going to be on the they tell us some points, right, that are going to be on the function graph. For instance, we know minus 4 and minus 5, that point's going to be on the graph, right? And 0 and minus 1, that point's going to be on the graph. And then also 2 and minus 4, that point is also going to be on the graph, okay? All right, so let's actually draw it here, right? So let's start with the first piece. We're going to graph this first piece, x minus 1, okay? Now, again, that's pretty easy to graph because that is a linear function. So it's not hard to graph linear functions, right? There's actually several ways you can go about graphing them. You might want to think about what the slope is, right? What is the slope for that line? 1, right, okay? So, you know, that information can help you in making the graph. But also, you just need to have 2 points, right, that are on the graph of that straight line. And then you can just connect those 2 points, right, okay, with a line, and that will also give you the graph. Well, I think we have 2 points, right, that we know are going to be on this line, because remember, we used this formula, correct, when we were evaluating f of minus 4, and we also used this formula when we were evaluating f of 0. Right, we use this formula, correct? So that means these 2 points are going to be on this line. So we can just plot those 2 points, right, and connect them with a straight line. So that's got to be pretty easy, right? So let's see, the first point there is minus 4 and minus 5. Let me see if I can get that in the right spot. So I think it's right there, right? There's minus 4 and minus 5. And then also 0 and minus 1 right there, right? Okay? And now we just want to connect those points with a straight line. Here's now where you have to be a little bit careful. Normally when I'm graphing a line, for most lines, you know, the domain is going to be all real numbers, right? So, you know, I like to, when I graph a line, I like to make, you know, make sure that I draw the line all the way across my graph. Because I want to make it clear that the domain is all real numbers. And that's true for most linear functions. But that's not the case here, right? Because what is really the domain for this piece, x minus 1? Not negative 4 to 4. Yeah, greater than or equal to minus 4, okay, and less than 2. So the domain there is really between minus 4 and 2, okay, for this piece. So when you're drawing this piece of the graph, this line, it can only extend between minus 4 on the x-axis up to 2 on the x-axis, all right? So you don't want to draw the line like this, okay? It's got to be limited, right? It's going to be restricted. All right, so let's do that. So I got to just erase here a little piece of this line, right? So let's come back and erase. It starts at minus 4, correct, right? So I can take off this piece, right? The piece there less than minus 4. And then it only goes up how far? To 2, right? So so let's take this off up here at 2, okay? So I'm going to cut it off right there at 2. All right, now let's see. What about the second piece? Okay, so I do have. So this is also a straight line. The slope is minus 2, right? But I already know a point that is on this line because remember I used this formula to evaluate f of 2. So this point is going to be on the line minus 2x. So let's plot that point since I've got it. So let's see, what's that point? 2 minus 4, correct? So 2 and minus 4. So notice this graph is going to look a little bit funny, right? Because you're going to have two pieces here, and apparently they're not going to come together. They're going to be a gap between them or a break between them. That sometimes happens with piecewise functions. Okay, the pieces don't necessarily match up. All right. Now, to plot the rest of that line, though, I need either another point, right? Okay, because I've only got this one point. 2 minus 4, but I can also use the slope, okay? So you can create another point if you want to on this line. That's fine, and then just connect the 2 points with a straight line. But just to be clever here, let's use the slope, because what's the slope telling me? It's telling me rise over run, right? So if I start at this point, let's see, minus 2 is the same as minus 2 over 1, correct? So if I start at this point, how can I get to another point using that slope? Not up to, though, Arthur, okay? Down to, right, because it's negative slope. So down to and then over 1. That will bring me to another point on the line. So that's easy, right? Go down to and over 1. There's a second point on the line, and you can actually get a lot more points on the line by just following that same pattern, right? All of those points are going to be on that second line, minus 2x. All right, well, now let's connect those with a line. And again, we have to be careful about the domain here, right? So what is the domain for the second piece? I don't want to draw the line too far. Greater than or equal to 2, so it's got to start at 2. So, okay, so I did that right. And then where does it end at? At 4. Did I stop right? No, I haven't gone far enough, right? Okay. So, I didn't draw my line right, okay? I miscounted my grid points, okay? I thought this was 1, but that's actually 1/2. Oops, let's draw that, let's redraw that, okay? All right, so let's try that again. I'm going to go down 2, so that would bring me to minus 6, right? And then over 1 right there, okay? See, minus 4, if you go down 2, that brings me to minus 6. Over 1 would bring me to 3, which is right there because of the way I drew the scale here, right, of the graph. All right, well, I'm not going to draw a third point now, but let's connect these with a straight line. Okay, now where do I have to cut that off, though? At 4, right, okay? So where's 4, right? There, okay? So let's erase there to 4. Did I get that erased far enough? Okay, that's all right. Okay, so that's basically it. So you get kind of this a strange-looking graph, but that is the graph of a function. Well, in fact, it's the graph of this piecewise function. Now, however, I need to improve the graph slightly, okay? Because suppose that I'm looking at the graph but I don't know the formula, all right? So I'm looking at the graph of the function, but I don't know the formula for the function. Remember, the graph and the formula are supposed to be equivalent. They're supposed to be equally useful. So how would I look at this graph and decide what f of 2 is, right? If you didn't have the formula and you were looking at the graph, just the graph, and you wanted to know what f of 2 is, right? Notice you have a little bit of a problem here, okay? Because you look at the graph, here's 2 on the x-axis, right? Okay? There's 2 on the x-axis, and so you're wondering, what? Is it down here, or is it up here? So we have to make that clear to the reader what is the correct value there, okay, for f of 2, all right? All right, here's the way we do that, okay? Which piece of the formula there was I really supposed to use to evaluate 2? The second one, right? Okay. So that means the correct value for f of 2 is down here, not up here on this line. Okay. Remember, that's the graph of the first formula. So the way you're going to indicate in your picture, there are other ways of indicating this, but one standard way of doing that is to come here and put an open dot right there above the 2 at that piece. Okay. So that would terminate the first piece, but it would indicate that, oh, yeah, that point is really not part of that line segment. Okay. So if someone looking at this wants to evaluate f of 2, they would know, oh, okay, I'm not supposed to read this value off the graph. I'm supposed to look at this one. Notice here I have a closed dot, okay, instead of an open dot. There's one other thing I need to do here, right? Okay, I need to terminate the graph right there, because remember, the domain of the graph stops at 4. So I'm also going to put a dot right there. Is it going to be open or is it going to be closed? Closed. Why closed? What? Right, okay. Because where does the domain stop at? 4, including 4, right, okay? The domain includes 4. See, here, where's the second? Yeah, see, x can be less than or equal to 4. So beneath the 4, we need to put not an open dot, but a closed dot. If you put an open dot there, what you're indicating is the domain stops at 4, indeed, but does not include the 4, all right? So you want the graph to accurately reflect the same thing as the formula shows, right? Okay, because you want these two to be, well, as equally useful as possible. All right. Now, of course, there are always drawbacks to graphs, right? But likewise, there are also drawbacks to formulas as well. Okay, so they may not be completely equally useful, but we want them to be as close as possible to one another. Okay. All right. Now. That's easier sometimes said than done. Graphing piecewise linear functions, and also sometimes even evaluating piecewise linear functions. All right, so now we're going to try this, okay? So that's the point of our worksheet today, right? Okay, because you really need this practice before your homework, but also especially before the test next week, because this is on the test. So if you look at the sample test, you'll see this is on the test, right? Okay, so we have two different problems. They're kind of opposite of one another. The first page is you're given a piecewise function. It's only got 2 pieces to it, right? You want to evaluate it for some inputs. That's pretty easy to do. And then you want to make the graph, just like we were doing in this example. So we want to see a graph of this function there. And then the second page is the opposite. So there we have the graph of a piecewise function. This one comes from a practical situation. We have a graph of a piecewise function, and we want to take that and write down the formula. Okay, so this is the very typical exercise in this class, right? Take a function formula, draw the graph, or vice versa. Take the graph and write down the function formula, okay? We like to be able to go in both directions there. All right, so that's what we're going to try first. And so Taylor and I are going to help you with this, right? So we'll answer questions, okay? And then we'll take a look at our work here, right, and see if we think we got the right answer. Okay, so let's start with page 1 first. But if you finish that one quickly, then of course you can go to the back, okay, and work on that as well. So follow those directions, right? Try to evaluate the a piecewise function, and then see if you can make the graph. It's going to come out looking. I don't know if it'll look like this, but it's going to have 2 pieces like this example. And both are going to be straight lines, okay, right? So if you can graph 2 straight lines, you can do it, okay? It's a week from today. Yeah, okay, right. So the sample is posted. I'll put I keep forgetting to put announcements in my math lab, but it's a week from today. Stopping here, this is the last topic on the test, okay? We will do some review on Monday, but we'll go on to the next section. But that section won't be on the test. Actually, we're going to go on to that today, but it won't be on the test. So the test is, well, you'll see from the sample test, it's almost entirely about straight lines. Everything you ever wanted to know about straight lines. Hmm? Oh. Do you have a front and not a back? If you have a blank, oh, if you have a blank back, we have a back page for you. Okay. We get. All right. Hmm? It's gotta be correct. I don't know, as long as those lines are correct. Is that? Yeah, 6 and 8, and it's gotta be right. Hmm. Hmm. You're gonna graph both pieces, right? So both pieces are part of the graph of that function, right? Okay. But this piece, you're only going to graph where x is less than or equal to 4, right? Okay. Because that's what this is telling you. This piece only applies when x is less than or equal to 4. And this piece you're only going to graph for x bigger than 4. Because that's what this second. You can, but then you're going to have to. You can, but then you'll have to erase part of it possibly, right? Because you can only have it for x less than or equal to 4, right? Okay. But you might help yourself by these are the same functions, so you can evaluate first, and that will give you some points, right? Okay. Yeah. Mhm. Okay, so you got these. All right. So which piece is that? This one. This is x minus 2.
This was oh no, this one was 0 minus 2, and then this one was 4 minus
4,
4 minus
right? Okay. So let's see all right, so which formula did you use? This formula?
Yes,
And then
and
all right, so you use this formula, right? So you connected those 4 and negative 8, but how'd you get negative 8?
4 minus
Yeah, right. It's only 2, right? Are you going to be able to erase that? Is that, oh, that's a pin?
Yes, pen.
Okay, all right, yeah. The reason I was suspicious, right, is because what's the slope of x minus 2? No, that's the y-intercept.
Oh,
So what's the slope?
0.
No. Where do you always find the slope from a linear function? Where does the slope always appear?
On the x.
On the x, right. So 1, right. 1 is positive, though, right? So you know that line is going to be doing what? Going up. But see, you had it drawn going down, so that was already a dead giveaway that something was off, right? All right, so you just have to connect those two, right? Okay, yeah. Now, let's see. This piece stops at 4, right? But notice it doesn't have a lower bound, right?
So it's the other way.
Yeah, so it's going to go, yeah, it's going to keep going, right? Yeah, there you go, right, okay. Now, where's the second piece? Let's see, this is on the second piece, right? So you have 10 and minus 2, right, okay. And so there's 1 point, and how can you get another point?
I think you said 8 over 1?
Yeah, you could do this. Well, no, the slope is minus 1, right? Remember, slope always goes with x, right? Okay.
So it's minus 1 over 1.
Minus 1 over 1. So you could go, what, down 1. Is that going down 1, though? I think that's from minus 2 to minus 4, so that's down 2. Right? Right. And then over 1. No, because that's going from 10 to 12. Right there, yeah. Okay, there's a second point. You get another point by doing that again, Eduardo. So I think if you go down 1 over 1, you'll get to this point. Down 1 over 1, you'll get to that point. So there's the third point. Now connect those with a line. But now, how far does that line go on this side? Where does this domain start at? No. And this is x bigger than 4, so it goes here, but on this side, where does it end at?
Stops at
4. So draw it to 4.
This is the y, I mean the x, right? That stops right
Yeah. But so draw it up in a straight line until you get to 4. Right there somewhere, right? Okay. Now we're back to this situation of which is the correct value for f of 4. But you already calculated that, right? It was this one, correct? Not this one. So how do you show that on the graph? There you go, right. There's the picture. Does that make sense? Right. Think you can do that again? All right. Okay, you're going to have a chance in your homework, right? And also on the sample test. Now you got to go backwards. There is the graph. What would that formula look like? Okay, right? So show Joshua and Montel, right, what you did to generate that picture.
Okay, so we have.
Okay, yeah, that's nice. I like that one.
So does that make sense then? Because if it's
I think so.
less than or equal to 4, that means it's definitely 4, which is the dark circle, and then it just continues on.
Yeah, and 0 was minus 2 right there, right? Now what about this piece?
Oh, no, I was just trying to make sure if I had that.
Yeah, that piece, yeah, but now I'm asking you, what about the second piece?
It's going to be 10, negative 2.
All right, so there's 1 point on there.
10, negative 2.
Right. Now you need either another point on that piece, or you could use the slope to make the graph. But you can get another point really easy. Just plug in another value for that's in the right domain, right? Which is what? Bigger than 4. So pick an x value bigger than 4, plug it in 8.
Yeah.
So what would that give us?
8 minus 8, 0.
0,
So
yeah.
just right here.
Right there, yeah. All right, now connect those with a straight line,
Yeah,
right?
well, I guess you could also just follow the.
You can also follow the slope, right? Yeah, okay.
Because with this, I'm pretty sure it's less than 4. That means it goes up, what, like right here? And then
Yeah, I think, right? Is that right?
it would be an open circle, I think. Because it.
Oh, be careful.
Oh, wait, no.
Let's see.
Yeah,
I
yeah.
went. Oh, yeah.
Yeah,
Right.
yeah, that's
Okay.
right. Because it doesn't include 4.
Right. Ah, so there's an ice. Right. I like that. Okay. Yeah. Pretty. Yeah. There you got it. Yeah. Now helps them. Right. Okay. That's right. Extremely good eye-hand coordination. All right. So help Uni and Chris finish that graph.
Okay, that makes sense.
All right. So I see.
Coming back to us, mister. I
Yeah.
forgot.
Wait, okay, am I not doing
Okay.
this right?
No, yeah, es que, mira, esta es 10, and this one is going to be smaller than.
Yeah,
It's
yeah,
going to be
yeah,
bigger than 4.
yeah.
So
No, but
that
I
one.
did. I just.
Right. So all right. So you got these points plotted, right, from
Yeah,
these
yeah.
two.
Yeah.
Now you want to connect them with a line. So you just connect them with a
Yeah.
line, but be careful. The line only is going to extend to where? Where does it stop at?
Oh, it's gonna stop at
4,
Yeah,
right.
4.
So when you draw it, don't include that point because it's got to stop here
Yeah.
at 4. So you're only going to get the
And
the left half.
that has to be opened, right? The dot.
No, I think this one is closed, right? Because f of 4 is
So, but
2,
it does
right?
matter, right? If they're closed or open.
Yeah, it does, right? It does, yeah,
But in
okay.
this case, like, is it being affected by anything? Do we have to look at this to determine the openness? Or
Mm-hmm.
the okay.
Yeah, but this formula includes 4, right?
Yeah.
Because so this will be closed. All right, so just connect those with a line, but leave that point off because you have to stop at 4, right? Okay.
Thank you.
Yeah. Now you do the other piece, right, Ben?
So it's only 2 points.
Yeah, well, that's all you need to draw a line, right? This is a linear function, correct? So connect those with a line. Yeah, you can do it by hand. It's not. There you go. Great. Nope. You went. Yeah, you screwed it up. You went too far, right? Because
Oh, it stops at.
stops at 4, right? Okay, so scratch through that. Unfortunately, you cannot erase it, so we're all right. Now do this piece, right? Do this piece, but where does this piece start at, Ben? What is that telling you?
The, it goes on. Like,
Yeah, but it tells you x has to begin at for the second piece. Where are you going to get at on the x-axis? You only have numbers what? Bigger than 4, right? So it's this piece starts at 4 and continues on. You want x values greater than 4, so that would be starting at 4 and going greater, right? Okay? Yeah. But that's also a line, so it should be pretty easy to plot. What does y'all's picture look like? Oh, that's nice. Okay. So, whoops. You got
You saved it.
a bad start there. What were you thinking?
Right here. What was it? Oh, this one. When you flip it, this is gonna be a negative.
Okay, yeah. So that piece is going down. That piece is going up. That's good. Now, can y'all do the opposite direction, which is take the formula, take the graph and write down the formula. So here's the graph. What's going to go into that formula? This is good, but you're not cutting off here, Skylar, because this says any x less than or equal to 4. So that would go all the way down to infinity. And this says any x bigger than 4. So that would go all the way this direction. Yeah, so don't cut it off there. That graph was cut off, but this one is not going to be cut off. All right. So nice. Yeah, that's
Okay.
good. Now,
Okay. And I
can
didn't.
you
Okay, so we.
now can you do this?
Okay.
Okay. Can you go the other direction? I think you can.
Okay.
Because you've got two lines here, right? So what's the formula? What's the formula for this line, right? Okay. Those are going to go in here. The boundaries, I think, you can write down really easy. This first piece extends from what?
Is that like
Does it start? Or is that line set?
is that 30?
No, on the
no.
x-axis.
Oh, the X.
Yeah. What's that on the x? 6, right.
Okay.
So this would be 6,
Okay.
right?
Uh-huh.
And does it go up to this piece?
8.
8.
Uh-huh.
So this is
okay.
8. Right. What about the second part? Start.
Oh, start.
8.
Yeah, 8 and
8.
then ends at 10.
Yeah.
Okay.
So there you go. 8 and 10. Now, so you got the boundary values there already. Now you just have to. So you know how to do this. What's the formula for the line that connects these 2 points?
Okay.
You'll have to estimate what these points are.
Okay.
And what's the formula for the line that connects these 2 points?
Which is also an estimation of.
Yeah, you'll have to estimate what these points are. That
Okay.
looks like this one is like 8 and something a little bit more than 36, right? So
Yeah, 8 and. It looked like it's on the line exactly, huh? Or no?
well, if you think
yeah.
so, then just write it down.
37
Well,
maybe.
okay, maybe, all right.
Okay. So
Okay.
8 and 37.
All right, so got the boundaries. Now, can you fill in the points? A little bit below 28, though, right? This one's a little bit below, so I would slide. It's not down to 27, maybe.
28.8.
No, not 28.8, 27.8. Right, yeah, something like that. Right. Try to read it as closely as possible to get a more accurate formula. All right, so you got the boundary values. Now you just have to fill in the formulas. So what's the formula for this line? And what's the formula for this line, right? You know how to write down formulas for lines, though, right? You have to calculate first the slope, and then you can use the point slope form, right, okay? But to calculate the slope, you're going to have to estimate what these points are. So you're going to have to estimate those coordinates because you can't read them exactly. So you just have to come up with an estimate. Get a good estimate, though, right, okay? All right, Ben. All right, so now you're going backwards. All right, so think about how we can gather information from this graph. I think the easy part is to fill in the boundaries because you got 2 pieces here, right? Yeah, where does this piece start and where does it end? Yeah, so you know what these are, right? Mm-hmm.
Were these not supposed to be right on 30 and 28?
I don't think so, no, yeah.
That's how I did it.
Okay, all right, well.
Well, I
Yeah.
think so. Okay.
Okay, all right, well, all right. That's fine. All right, now, all right, so you got the boundaries. Now you just have to write down the formula. So you want to write down the formula for this line and write down the formula for this line. But we've been writing down formulas for lines, right? You need to calculate what? To write down a formula for a line, you need what? The slope. So you'll have to, yeah. Well, you don't really need the y-intercept because you can use a point also, right? So, and we don't really have a y-intercept here, so we'd have to use a point and the slope. But you got to calculate the slope. You're going to have to estimate the coordinates of these points. So you're going to have to get an estimate for what the coordinates are here and here, right? And here, all right? So you'll just have to estimate. So different people might get some. No, you missed this one.
So I leave it alone.
What is negative though?
No, this one is not graphed right.
So I don't graph it.
No, you do graph it, but you didn't graph it correctly.
Does she connect it?
Yeah, it shouldn't be. It's not going to end up being connected.
Okay.
So like this,
Mhm.
right? Look, I even did this, Mr. Take
But you haven't graphed the second piece, right?
Oh gosh.
Yeah. Right. Okay.
No, look, it's right here.
Well, you have a point on it, right? But I need the whole line, right?
Oh, so you do want me to connect it? Oh,
No.
like
No, not necessarily connect it. Find another point on this line. How can you find another point on this line? Plugging in, right? So you can't plug in 10 because that's how you get this point, right? So what else can you plug in that's going to be on this second piece?
An 8.
An 8. So what happens when you evaluate 8? What do you get? What's f of 8?
We're gonna get 0.
You're going to get 0.
0.
So,
Right?
now connect those two.
Oh, wow.
Yeah, right, okay.
Okay, and then we make a line like this?
Yeah.
Okay, math. That's
Mhm.
math for you guys. Oh, jeez.
Now make sure you draw it far enough, though, because where does it start at? Where does that second piece start at?
4.
4. So extend it all the way to 4.
Okay.
Nice. All right. Now there you go.
Does it
See,
have to
they
be
don't
open circle or
connect.
something?
Yeah, someplace you have to. Where's the open circle
It's
go?
gonna be right here in the
Right
line,
there.
right
Right. Yeah. And the reason it's an open circle is because this is greater than 4. Right. So this is not the right value for f of 4. This is the right value for f of 4. Now you got it. See, it's two pieces, but they don't come together.
Never.
They do sometimes come together, but not in. They come together here, but they didn't in this one. Yes. Okay. So you're coming up with 3x? I don't think so. So.
Use the point slope formula.
Oh, I see. So, yeah, that's nice, right? So you did 3x minus 6 plus 29.5. That's what you're going to put in there. That's it.
That's
The whole thing.
Oh,
Yeah,
we have to
right.
solve for it?
Yeah, no. Just put that whole thing in there. Yeah, just put that whole thing in
And then
there.
it will do the same thing for this one.
Yeah.
For this.
Where's this one? Where's the
We
second
haven't
one?
done
Oh,
it.
okay,
We're
yeah.
just
So,
doing
yeah,
it.
just write that whole thing in there. Yeah. You don't have to simplify it. Mhm. I think this one comes up a little. Well, you may have drawn your line a little bit too steep, but it's fine. All right. So see, his didn't come up quite as far as yours, but it may just the way you drew the line. So that part, Joshua, right, is not supposed to be there, right?
Yeah.
Because this part is supposed to stop right here. Yeah. Okay. Nice. Now, can you do the this? Oh, you got the bounds, right?
Yeah.
So you're off to a good start. Now you just have to fill in the formulas. So what's the formula for this line? And what's the formula for this line? You know how to write down formulas for lines, though, right? We've done that so many times. What do you need to write down a formula for a line?
2 points.
2 points, right, to find the slope. So you're going to have to estimate the coordinates of these 2 points. And then once you've got the slope, you can use one of those points and the slope to write down the formula for the line, right? Remember, it's y equals m times x minus x coordinate of the point plus the y coordinate of the point, okay? There, that's it, right? So just have to do a little bit of arithmetic there. Did you finish it?
This one, is it this?
I'm not sure, but probably right. You estimated this is 10 is 27.5? No, this point?
Yeah.
Oh, yeah, perfect, right,
But
okay.
it's a negative, so it will be negative.
Oh, yeah, where did you calculate the slope at for this one?
Oh, I just did the little thing like this.
Oh, well,
I don't know if it's right or wrong.
oh, so you went from 27, you said that was 27.5 up to, you said this one was what?
36.
No, I think that's
There.
okay, right, all right. So once you get the coordinates for this one estimated right, okay, then yeah, you can use the slope formula, right? But your technique also would work, but it's hard to figure out what this is, right? it may be close to 7/2. The 2 is correct because you're going from 8 to 10. So the 2 is right. I don't know if the 7 is. I don't know if the 7 is right.
Twos. So it was 2, 4, 6, 8.
Right. Okay. So write down the coordinates there next to your point, and then use the slope formula, so you don't have to worry about counting and miscounting there. Are they getting it? Are we getting? No, that's fine.
I just need help with an example, and then I can go on and live, you know?
Okay, so we had an example on our notes last time, right? But that's fine, because you know what to do here, right? From the previous example. These are supposed to be the boundaries, right? So what's the boundary of this piece? Where does it...
6. This one's 8, right?
Right, so what's this piece?
8, and this one's 10.
Perfect, right, okay. So you got those right. Now, these are the formulas. So you want to write down the formula for this line. That will go there. And the formula for this line goes here. But you know how to write down formulas for lines because you've done that a lot, right? You find the slope, and then you have a point on the line. So you can use the point slope formula to write down the formula for the line, right? Okay? Yeah. Uh-huh.
We guesstimated 2 points.
Mm-hmm.
Came up with 6, 25, 49, and then this is with 4, 6.
Where did that come from, though?
I plugged it into my calculator on edit. And I did that, and then I
Oh, and it told you? Okay. Yeah, well, we are. So, yeah, oh, that's great. That's great. So, so TI's engineers are really smart, but you need to be just as smart as them. All
well,
right?
I know how to do it. It's just one more work.
Oh, well, do it then. Yeah, I want to see you do it. Right. Okay. Yeah. So calculate the slope, and then use one of those 2 points in the point slope formula. Yeah. You don't have to simplify it. Just plug it into the point slope formula, right? Slope times x minus x coordinate of point plus the y coordinate of the point.
Isn't it a little bit more simple to just calculate the intercept?
No. Well, you can. But I don't think it's simpler, right? I don't think it's simpler. So calculate the slope for me. Calculate the slope. So Chris, are you calculating the slope there? Using your slope formula. You also did you estimate that point? All right. Yeah, right. Okay. Now, so y is equal to 3.5. No. Well, oh, you're going to do it like this. All right.
It's just the way I've been taught.
All right. Well, let me show you the fast alternative, right? Which is sort of all of the steps of finding the y-intercept sort of incorporated.
Like y
equals 3.5, and now in parentheses, yeah.
Y1.
Right, but what's x1 here? Pick one of your
6.
points. 6, right? And what's the y1 for that? 29.5. And you can just leave it like that. You don't have to simplify it. So that you can just write in here. I think that's pretty fast, isn't it?
Yeah, I guess so.
Right. Oh, don't write y equals, because this is the same as y equals. All right. So, Chris, we want to find the formula for this first line, right? But we know how to do that, okay? Because we have estimated 2 points on that line. So we calculate the slope using our slope formula from these 2 points. And then once you know the slope, you're really ready, because when you know the slope at a point on the line, you can write down the formula for the line using the point slope formula. So that's the steps that you want to go through, okay, right here. What are you looking at? Is there any? Okay, yeah. All right, so just write that down, right? Okay. All right, so did you calculated the slope, right? You got 3.5, right? Now you need so now you're done, because now you can write down the formula really easy. It's going to be y equals So write this down, y equals, and then it's the slope, 3.5, which you calculated, right, times in parentheses, x minus the x minus the x coordinate of one of the points that you used, either one. So you want to use this one, okay, close parentheses, and then plus the y coordinate of that point, plus the y coordinate of that point. So that's it. There's your formula. Just that easy. So you don't have to copy the y equal because that's this. So just put that in there. That's it. Now you do the same thing for the second line.
So why is that one different than this one?
Because this is a different function. Yeah, these are two different functions, right?
Because
Okay.
they've been the same, kind of.
Huh?
They've been the same, so I thought they were going to end up like this. But okay.
Well, it did end up like that. That's a linear function. I just didn't simplify it. I didn't multiply the 3.5 times the x and the 3.5 times the 6. So I didn't. That is a linear function. Yeah. If you multiplied out the 3.5, it would come out looking like something like this. Not the same numbers, of course, but something like that, right? But you don't have to do that, okay? Because there it is. That's a formula, okay? Did y'all get it written down?
Yeah. 8.5 over 2.
Oh, 8.5 over 2. All right. Okay. So, and nice, right? So there it is. Yeah. So there's your formula for that piecewise, right? Okay.
Oh, like you need to use a different slope for that, right? Okay.
This is going down.
So there's your first one, and that's your second one. Oh, you just simplified. Yeah, you actually really could have left it just like that. Yeah. Unless it says simplify, you could just leave it like this. Okay. Yeah. As far as I'm concerned, I don't know. The homework is sometimes picky, so it might have. Yeah. Right. I'm a little bit less picky than the homework. Okay, let's stop in about 3 more minutes. Y'all are getting really close. Really close. See if you can write that down. Mm-hmm.
Well, I had done it wrong earlier. I did it this way.
Mhm.
I was looking at it to try to understand the problem better. I noticed that the arrow was pointing this way for this one, and my line pointed this way.
Oh,
and then
well.
this one pointed this. Is that like a good way to think about it?
Unfortunately, sometimes not, because you might have this written as the other. This is the same. That's the same inequality as this one. So it could have been written like this. Yeah, right. Rather than and then, so I'm not sure what there probably is a shortcut there, but I'm not sure what it is. You need to think about, I want numbers less than or equal to 4. Where are numbers less than or equal to 4, right? Okay. Those are over here on the to the left of 4, right? Yeah, okay. Did y'all get your formulas? Looks nice there. Okay. Great. Think y'all can do? Did y'all get the formulas written down? Okay. Do y'all think y'all can do that on a test? Well, that's right. So there's homework for this, right? Okay. So you'll get more opportunities to try this. Okay. Okay. So I see most people are done. So does anybody have any last questions there? I think most people had written down the right answer for that one. What? Yeah. Choose a coordinate from the line that kind of fits. What?
It's not like given like this one.
You can choose any point. Oh, you can. Right. Okay. So you could have picked any point on the line, not the end points of the line segment. You could have picked any point on the line segment and used that. Right. Okay. That is. We mentioned that, but that's an important fact that the slope of a line is independent of the points you pick off of the line. You will always, no matter what points you pick on the line, you will calculate the same slope, okay? That's really fundamental to straight lines, okay? All right. Okay, so we're going to turn those in, and I'll add that as a grade in your homework grade, okay? In the grade book. All right, let's take a few minutes here. So let's take about 5 minutes, and we're done talking about straight lines. Hooray! So let's take about 5 minutes, and then we're going to talk about another kind of function, almost as important as straight lines, but not quite. Okay. So that will be our next subject that we want to tackle. All right. So we'll start that after we take a few minutes here, okay? I'll see y'all in 5 minutes, right? Okay, y'all are free to. Okay, let's resume here. So I switched notes because we're moving into chapter 3. But we're still talking about functions, but a new type of function is called quadratic functions. So I know you've heard the term quadratic before, and but that's usually in relations to equations, quadratic equations, and the famous quadratic formula, which is going to come up here soon, because quadratic functions are closely related to quadratic equations and the famous quadratic formula. But let me just give you, we have to start here with a bunch of terminology and some definitions, just some basic facts about so-called quadratic functions, which are kind of similar to linear functions. It's kind of one step up from a linear function. So if you have a function formula that it can be written as like this, okay, in this format. It doesn't have to be written in this format, but if it can be simplified to this format, then that is called the quadratic function. So the x here is the input variable. The a, b, and c are going to be just number coefficients that are going to vary from function to function. So you get different quadratic functions by varying these coefficients. The b and c can be 0 here, but the a cannot be 0. We don't want the a to be 0, because if the a is 0, notice what happens is this term will disappear, and you end up with a function that looks like that. What sort of function is that, though? That is linear, right, okay? Well, we already know about linear functions, so we don't want to be talking about linear functions. So we're going to insist that this coefficient on the x squared term isn't 0, so we don't have a linear function. So quadratic functions are closely related to linear functions. It's kind of just one step up, or one step more complicated than a linear function, because in a quadratic function, the real distinguishing characteristic is you have this term where you have x squared, the unknown squared. See, in linear functions, the x is only raised to the first power, but if you raise x to the second power, one additional number in the exponent there, then you get instead of a linear function, you get a quadratic function, all right? So when you graph a quadratic function, you're not going to get a straight line, all right, okay? Not going to get a straight line. You get a different sort of curve. You do get a characteristic curve, though. It's just not going to be a straight line. That curve, by the way, is called a parabola. Another term that I know you've heard before, and we'll look at several examples of parabolas and what they look like. They're not complicated curves, but they're not straight lines. All right, so a little bit more terminology here. This coefficient a that's attached to the x squared here, that's multiplied by the x squared, that's called the leading coefficient of the quadratic function. kind of obvious why, right? Okay, because if you write the quadratic function in this form, the a is going to be the first coefficient you see, right? So a is the leading coefficient, and a number here that's added at the end, that is called the constant coefficient. So notice that's not multiplied by x there, so that's just the constant. The coefficient that I've labeled b here, as far as I know, doesn't have a special name. I bet it does, okay? But I don't happen to know what that is. All right, that's probably lost in the obscure history of mathematics. What the name for this coefficient b is. We can call it the middle coefficient if we like. All right, but it doesn't have a technical name that I'm aware of, all right? So leading coefficient and constant coefficient, and the leading coefficient cannot be 0, okay? You don't want the leading coefficient to be 0 because then you won't have, you'll just have a linear function in that case. All right, so again, I already mentioned, right, when you graph a quadratic function, you get a curve called the parabola, and it's going to have a bowl shape to it. So you get a bowl-shaped curve like this. These are very rough sketches of parabolas, all right? So it's kind of like a straight line that has been bent in either bent up or bent down. So not a complicated curve, but not a straight line, right? So notice that parabolas are not always increasing. They're not always decreasing. Lines are always increasing or decreasing, right? Or they're completely flat. But parabolas are sometimes increasing and sometimes decreasing, okay? This point on the parabola that's either at the bottom of the parabola or the top of the parabola. In other words, the point where the curve switches from increasing to decreasing or vice versa, that's called the vertex of the parabola. So when I refer to the vertex of a parabola, you'll know what I'm talking about. It's that top point or bottom point of the parabola. Top and bottom are not really rigorous mathematical terms. So it's the point on the parabola where it switches from increasing to decreasing or vice versa. Now, some information about the graph you can determine just from looking at the formula. So you won't be able to, just from looking at the formula, tell everything about the graph but immediately. But some things are very easy to determine just from a quick glance at the formula. So one thing is the leading coefficient is going to determine how that parabola opens. So if the leading coefficient is positive, remember it can't be 0, but if it's positive, that means the parabola is going to open up like this, okay? But if the leading coefficient is negative, then the parabola is going to open down like that, okay? So when you make the graph, you'll know beforehand from the leading coefficient whether you're expecting the parabola to open up or open down. Kind of like you can tell from the slope of a straight line, right, whether the line is going up or going down. From the leading coefficient of a parabola, you can tell if it's opening up or opening down, okay? Another thing that's really easy to determine is the y-intercept. Just like with straight lines, it's easy to figure out what the y-intercept of a parabola is because it's always going to be the constant coefficient. Whatever that constant coefficient is, that's the y-intercept. That's so easy to see because if you plug 0 into a parabola, you're going to get a times 0 squared, whatever a is, plus b times 0 plus c, right? Because that's what formulas for parabolas look like. So you would have a times 0 squared if you plug 0 in for x, plus b times 0, and those two terms will disappear, and then you'll just get c. So you know that the y-intercept c is going to turn out to be always whatever that constant is. So you know where the parabola is going to cross the y-axis. Another thing that's really easy here is the domain, okay? So the domain for quadratic functions is like for linear functions. Unless there's some sort of restriction based on how the function is being used in practice, the domain will be all real numbers. So you have a nice big domain for quadratic functions, just like you do for straight lines. there's actually some better graphs of parabolas, okay? So again, here's a parabola that's opening downward. When I graph this one, I'm not going to show you the formula, but when I graph this one, the formula involved the leading coefficient of -1/2. So you can see that the parabola is opening downward, right? Okay, and this one, when I graphed this one, this had a leading, I don't know what the B and C were, but this one had a leading coefficient of 2. So see, that's positive. So that parabola is opening upward, right? Also, from the leading coefficient also controls not just whether the parabola opens up or down, but the size of the leading coefficient also controls how wide or narrow the parabola is. So when the leading coefficient is a big number, bigger than 1, the parabola is going to get narrower. It's going to be progressively narrower. But if the parabola is a small number, a fraction, between 0 and 1, the parabola is going to be fatter, okay? So if you get a leading coefficient close to 0, you're going to get a really wide parabola. Still be a parabola, but it'll be really wide. So see this one much wider than this one, right? Because this is if you look at the absolute value of the leading coefficient, that's 1/2, which is a lot less than 2, right? So the bigger the leading coefficient, the narrower the parabola becomes. Now, here's the other key fact, all right, okay, that we're going to use a lot. We can also determine from the formula where the vertex is, okay? So we can figure out where the vertex is, and that takes a little bit more work, a little bit of work, but not a lot, okay? So it turns out that the x-coordinate from the vertex, the x-coordinate of the vertex, so that's where that parabola switches from increasing to decreasing, right? That's always going to be located at this place on the x-axis. So here's the formula for the x-coordinate of the vertex. You just take minus b, that's that middle coefficient, over 2a. Notice it's minus though, right? Minus b over 2a. That will give you always the x-coordinate of the vertex. How can you find the y-coordinate of the vertex? If you know the x-coordinate, how can you then find the y-coordinate of the vertex? If you know this, what do you have to do? Do what? Plug it into where? Yeah, Emiliano, where are you going to plug it in? Into your formula, that's correct, right? You plug it into the formula. You always do that, right? For any function, if you know the x-coordinate, you can find the y-coordinate by plugging the x value into your function formula, right? Well, that's true for quadratic functions as well. So the y-coordinate of the vertex, is going to be f of minus b over 2a. Take your x-coordinate and plug it into your function formula. That is extremely useful information, okay? If you know where the vertex is, and you know if the parabola opens up or down, and you know that from the leading coefficient, right? If it's negative or positive, then you already have a good idea of what the parabola is going to look like. That's maybe not enough information to draw the graph accurately, but it certainly gives you a good mental picture, right, of what the parabola is going to look like. So there's our scheme for always finding the vertex of a parabola. You got a formula for the x-coordinate, and then take that x-coordinate, whatever you calculate here, minus b over 2a, plug that into your parabola formula, and you'll get the y-coordinate also of the vertex. I have that in the notes there, okay? So there's the vertex formula. And this is the only part that you really need to recall, right? Minus b over 2a, because this is easy to remember, right? You always find the y coordinate that matches an x coordinate by plugging it into your function formula. That's true for any function, not just parabolas. Okay, right, so that's kind of a quick summary of important facts about parabolas. There's a few more that we want to add, okay? Let's add one right now, actually. How would you find the x coordinates? I'm sorry, the x-intercepts of a parabola. So I told you how to find the y-intercept, right? That is always c. Okay, the y-intercept is always the constant coefficient c. But how would you find the x-intercepts of a parabola? Where the parabola crosses the x-axis. By the way, parabolas don't always cross the x-axis. Notice this one does not cross the x-axis, right? Because its vertex is above the x-axis and it opens upward. So that means it's never going to cross the x-axis. But this one does cross the x-axis here and here. How could we find those two x-intercepts? In general, how do you find the x-intercepts for any function? Parabola or not? What's the scheme? What? Plug 0 in for y. Exactly right. So plug 0 in for y, not x, but y, right? So in a quadratic function, when you plug 0 in for y, you're going to get 0 is equal to, well, the function formula, right? Which is ax squared plus bx plus c. And then what do you have to do? You have to solve that equation, right? So solve that equation, and that will give you the x-intercepts, okay? So solve to find the x-intercepts. Just take the formula, set it equal to 0, and solve that equation to find where the parabola crosses the x-axis. Okay, so we need to practice, but we'll practice that. We'll get plenty of practice with that in some upcoming examples. That's right. So you may end up with two solutions to this equation, okay? Yeah, you may end up with two different solutions to that equation. You cannot have more than two x-intercepts, though, right? Yeah, think about just the nature of the curve. There's no way you could get more than two. You may have none, and we saw a picture of that a moment ago, and you could have exactly one. How could you get exactly one, Arthur? So what parabola would give you exactly one x-intercept? Well, it would have to be the case. Narrow? I don't think it matters how wide it is, but it's got to be positioned just right. How would you position it so that you would just get one x-intercept? This one gives you two, right? Of course, that one gives you none. So how could you position it so that you get exactly one? When the vertex is on the x-axis, right? Okay, so if you have a parabola where it just so happens that the vertex is on the x-axis, like maybe this picture, right? Okay, then you're only going to have one x-intercept. It's going to be right at the vertex. Okay, so it's possible to have two x-intercepts, one or none with parabolas. Okay. All right. Well, let's just test our knowledge a little bit here of quadratic functions, what I just said. Okay, so the first question is easy. I just want to know which of these formulas really is a quadratic function and which are not. Okay, and then once we discover the ones that are, maybe we'll take a look at the graphs or a little bit more closely. All right, so what about A there? Is that a quadratic function? Yeah, that fits the format perfectly, right? You have x squared, and then we have this x to the first power. There's the constant coefficient, right? So that's definitely quadratic function. What's the leading coefficient there? What's the a here for this parabola? 2, right, okay. And the middle coefficient, the b, is what? What? -4. Yeah, be sure to include the sign with the coefficient. So the b is -4, and what's the c? -1. So when we graph this one, -1 is the c. So when we graph that parabola, well, of course, we're going to get a parabola, right? So you're going to get that curve. Which way does it open? Up, right, because the a is positive. When the leading coefficient is positive, kind of like when the slope is positive, right? When the leading coefficient is positive, the parabola is opening upward, okay? So the parabola is opening upward. What's the y-intercept? -1, right? Always the same as the constant coefficient, all right? So there's the y-intercept. All right, so let's take a look at this one. If I can get, see if I can get Desmos here to come on. Oh, so there's the graph, right? Okay, of that parabola, 2x squared minus 4x minus 1. So see, indeed, it is opening upward, right? Okay, there's the y-intercept right there at -1. Notice this one's kind of narrow, right? Because the leading coefficient is 2. All right, so the bigger that leading coefficient, at least the bigger the absolute value, ignore the sign, the bigger the absolute value of the leading coefficient, the narrower the parabola becomes, okay? All right, so Arthur, there you can see we have 2 x-intercepts. So that's going to, if we set that formula to 0 and solve, apparently we'll come up with 2 solutions there, right? Okay. Now, we can figure out this point, okay? That is the vertex, all right? So we can figure that one out. I can kind of see it here, though. What does it look like from the graph the vertex is? That would be, what's that x-coordinate of that vertex? 1, right? And what's the y value there? -3, okay? So it looks like the vertex is at 1 and -3. Let's check that, though. So let's go back to the notes here, and we're thinking it looks like the vertex is supposed to be at 1 and -3. Remember, the vertex is a point, okay? So when you write down the vertex, you have to write down coordinates. So we're thinking the vertex is at 1 and -3, but now we can check that, right? Because we have that vertex formula. So remember, the vertex formula says, that vertex is supposed to be at -b over 2a, right? That's the x-coordinate. And then whatever I get when I plug that into my function, that would be the y-coordinate of the vertex. So let's see, what's -b over 2a in this case? Well, b is -4, so you have minus a -4 over 2 times a, but a is 2. Does that work out to be right? Is that -1? Yep, not -1, but +1, right? Okay, so you get minus a -4, which is +4, over 4, which of course is 1. So we read the graph right there, and now let's find the second coordinate. So just take that and plug it into your function. So you're going to get 2 times, let's see if I can squeeze this in here, 2 times 1 squared minus 4 times 1 minus 1. So let's see, that's 2 minus 4 minus 1. Yep, that's -3. So our vertex indeed is 1 minus 3, okay? So -b over 2a turned out to be 1. F of 1 from that formula turns out to be -3. So we read the graph right. Okay, what about this second one now? Oh, I thought I had y'all fooled with that one. Okay, so that is indeed a quadratic function. It's just not written in the standard form, but you can put it into the standard form just by multiplying 2 minus x times 3 plus x. So you get 6, plus 2x minus 3x minus x squared. So you have 6 minus x minus x squared. And that is a parabola, right? What's the leading coefficient there? Leading coefficient. That's the coefficient of the x squared term. -1. What's the middle coefficient? That's the coefficient of the x term. What? Also -1. And then the c value, which is the y-intercept, is 6, right? So don't get confused because the terms are written in a different order, okay? Right? The leading coefficient is the coefficient of the x squared. So let's see, this parabola, when we graph it, is going to open downward, right? Going to open downward. It crosses the y-axis at 6. Let's see what that looks like. But we already have a good idea, right? It's going to open downward and going to cross the y-axis at 6, right? So there you can see it. All right, opening downward crosses the y-axis there at 6. So the vertex is just a little bit above 6 on the y-axis. This third one, so this is a quadratic function, right? This is also a quadratic function. Again, the dead giveaway there is the x squared term in the formula, right? So 9 times out of 10, if you have x squared in your formula, that's going to be a quadratic function. What's the leading coefficient here? One over 3, right, okay? So that x cubed over 3, remember, you can write that as 1/3 times x squared. So the leading coefficient is 1/3. That's positive, so this parabola opens up. What's the middle coefficient? 2/3, right, okay? And then the constant coefficient is 1. So this parabola is going to open upward when we graph it. And so it looks like this. So this one has no x-intercepts. Parabolas don't have to have x-intercepts, but the y-intercept we already knew was right there at 1, correct? And see, that's a nice fat parabola because the leading coefficient is 1/3. That's a pretty small number. That's close to 0. So you're going to get a wide parabola in this case. And again, we'll come back and compute this, but from our vertex formula, we can exactly figure out what this vertex is. I thought, yeah, so Desmos is trying to tell me the x-coordinate of the vertex is -1, and it looks like the y-coordinate is 0.667, which I think is 2/3. So we'll check that eventually here. All right, what about D now, on the other hand? So this is a trick question. Is that a parabola? So I don't sound convinced there. Is it yes or no there? No, right, okay. Don't get confused by the 2 squared, right? The square is not on the x. So the x is just raised to the first power. So what sort of function is this really? Linear, right, that is linear. Of course, you can write 2 squared as 4, correct? So we could have written this as 3 minus 4x, and pretty easy to see that's linear, right? The slope is -4, and the y-intercept there is 3. So this is not quadratic. What about this one? You have x squared, but be careful. Is that quadratic? No, it's not really quadratic, and it's because of the cube root. Let's take that and write that as an exponent. So how do you write cube root of x squared as an exponent without the radical? What power is cube root of x squared? Remember how you convert radicals to fractional exponents or vice versa? Where does the, in a fractional exponent, where does the type of root go? It's 2 over 3. Yeah, that's correct, right. Okay. This denominator tells you the type of radical, and remember, this exponent stays as a power. So the cube root of x squared is x to the 2/3 power, which is not the same as x squared. So x is not being squared here in this formula. So it's not quadratic, okay? X to the 2/3 is not the same as x squared. It's not linear either, all right? So that's a completely different type of function. So the last one, that one's pretty obviously quadratic, right? Because there you have the x squared. So again, what's the leading coefficient here? -1/2. That's easy to see. The middle coefficient is -1, and the constant coefficient is 2, right? So we can see when we graph this parabola, it's going to open down. So there it is, opening down. So it has a couple of there of x-intercepts. All right, so there's our a quick little introduction there to quadratic functions. Now, quadratic functions have, just like straight lines, they have lots of interesting applications. So we're going to try this one next time. This is a baseball application, so my timing is perfect. Wow, I hope the series is still going on next Monday, because if it's not, it'll be a disaster, right? So we'll try this one next Monday. This is a question about a little physics question. We pop up a baseball. We want to know how high is it going to reach before it falls again, okay? Turns out that to answer that question, you're going to use a quadratic function, all right? So in physics, it's quadratic functions that govern the motion of falling objects, okay? One reason that quadratic functions are useful to us. All right, so we'll try that one on Monday, okay? All right, so don't forget your homework that's due tonight, right? You got homework due tonight, so finish that up. Yes, turn in activity 5 for me.